guess since electricity is gone, there is no AC. Right? Perhaps we should leave the door open. So, let me see. So what we have done is, this is essentially a block which issues logic command to turn A top, A bottom, B top, B bottom, C top, C bottom, right? And then what we have is one PWM generator. Now this also is a clever PWM generator which is robust from convergence issues. And so the system here is that we have a command, a current command reference, and we have got here a type 1 amplifier. We have a limiter so that the command to PWM generator goes only from 0 to, let's say, 0.99, or 0.01 to 0.99. And then we have one PWM signal. And this PWM signal is ANDed with just the top switches, just the top AT, BT, and CT. And so you can see that only the top switches are PWM, AT, PWM, BT, PWM, CT, PWM. And the bottom switches are driven by direct logic, A bottom, B bottom, C bottom. So you could essentially think about pulses and signals coming in, and we are directly driving the lower switches.
So they are being driven by square wave or PWM?
Square wave.
So essentially square wave.
That's right. That's right. Right. The bottom is essentially square wave, and the top is being PWM. Okay. Now this is good for when you're using an 8-bit microcontroller, when you're trying to develop a very low-cost drive, when you are short on PWM channels. This you can implement using, let's say, a PMOS on the top and an NMOS at the bottom. So here, this is, we have got here also implemented sense resistor with R and C, and then we have, that's a gain block from PSpice, and that's a gain which is being fed to type 1 amplifier. Okay.
What's the R&C1?
Pardon me?
What is the reason for R2C1?
R2C1, basically the reason for R2C1 is to filter out the high frequency from the resistance. So it is because you're comparing with a DC reference here, so you want to essentially have a DC feedback.
Probably to block out the diode reversity code is spike.
That's one reason also. That's another reason also. Yeah. Because you really don't want. At the end of the day, you want to make sure that the currents in these coils, A, B, C, is going to be as per your concept, as per your theory. They needs to be flat, right? So you really want this sort of current. Now, you will not get this sort of current when you begin to run the circuit, because diodes, when you're transitioning from one coil to other coil, the diodes are going to suck up some of the current. And so you always have a dip in the middle. So right here in the middle, when you transition, from one phase to the second phase, there's a dip right in the middle here. And the more inductive your motor is, the bigger the dip in the current you're going to have. And that's where, if you have this kind of strategy, it will not work for highly inductive motors, because these diodes will eat you up, and output will not be. Output will have a lot of ripple and tremendous amount of losses because of reverse recovery of these diodes. Right. So I think this is we're at 10:33. So we're going to take a 15-minute break. There's some tea and coffee, and then we'll start at let's say about 10:45, 10:50, supporting her. I just wanted to thank them for their wonderful work, and now you can put face to the name. Thank you.
Okay.
Thank you, Ms. Lass.
Nice meeting you all.
Yeah, great opportunity, indeed. Okay, see you then tomorrow. Bye-bye.
All right. So let's, before we get into the actual circuit model, we'll go through some waveforms to get an idea of what can be done. So we talked about this circuit. And now this is how we have generated this is the gate drive logic. Now we have used 6 sources. These are V pulse source. So 6 sources to build essentially 6 simple square waves in PSpice. Okay, and what we have here is, if we just focus on this for a minute, VCT, you have got essentially V1, which is the starting voltage, and then you have got V2, which is actual gate drive voltage. And then you have a delay time, you have a rise time, you have a fall time, you have a pulse width time, and you have a frequency. So these parameters are defined in a parameter file. We'll show you in a minute what the parameter file is also. Now, we tend to store all of these parameters in a parameter file so that they can be easily changed. We can essentially perturb any of these parameters when we're running a simulation. Okay, so and as you can see, delay 1, there are basically 6 delays: delay 1, delay 2, delay 3, delay 4, delay 5, delay 6. So these delays sequence when these gate drives come on. Okay, and then the rise time and the fall time is how fast is the rise and fall of these square waves. Okay, and then PW is a pulse width of these square waves, which is 120 degrees in this case, and then the frequency is essentially the frequency of rotation of the motor. Okay, so and so you have A top, V top. You will see that the delay 1 and delay 2 are 180 degrees out of sync. Okay, and I'll show you the actual waveform in a minute. So the gate drive voltage we have set at 5 volts. The rise time and the fall time is set at 10 microseconds. Probably too much, but it's not too much for back EMF voltage. Actually, sorry, it's the logic. Yeah, so 10. I think it's 10 microseconds. And that's maybe too much. The rise time and fall time, and the pulse width, of course, is 120 degrees. Okay, so in this case, we have used a motor from Moog is the manufacturer. So we have used a frequency which is an odd frequency, 133 hertz is the rotation frequency. So the period is 1 by frequency, 1 by 133 hertz is the frequency. What else do I want to point out? And then delay 3 is shifted from delay 1 by 120 degrees. Delay 5 is shifted from delay 3 by 120 degrees. And so is the case with delay 6 and 4. They're shifted from delay 2 and by 120 degrees. So that's how we have set it up. So once you set up the 6 sources, this basically gives you 6 square waves. That's all it gives you, 6 square waves to drive your brushless DC motor. Any questions on this one?
Are these delays, are they entered one by one, or are they computed automatically somewhere?
They are. We set the first delay, and the rest is computed automatically. The delay one, because the delay one would be 0 if you were starting with the PWM when the back EMF was rising, right? But you have a 30-degree delay between. So when you are, here, let me. So this is your back EMF signal, and this is actually 180 degrees, and this guy here is 120 degrees. So this and this becomes essentially 30 and 30. So the back EMF voltage, this is what we're trying to simulate. So this delay 1 is your 30-degree delay. Then, so the rest are computed accordingly. Now we will also do an experiment where we change this delay 1 and we see what consequences are there when this delay 1 is not correctly, because it can vary because of manufacturing variations, and especially when you have low speed drive which you are trying to run with the BLDC, non-geared, then if it's not precise, then you have more issues in torque, ripple, and smoothness. Okay. So this is the definite. This is how we do back EMF model. Again, we use the same V-pulse model from PSpice, and I think a similar model exists even in Simplorer, if I remember right. Ashish, the similar model available in Simplorer too. Yeah. So we have got T-rise, pulse width, and T-fall. Now here, rise time and fall time, again, we make it such that you are, the rise time is 30 degrees and fall time is 30 degrees. The pulse width is 120 degrees. Amplitude is A, and then of course we have got motor inductance parameters and motor resistance parameters. So everything is parameterized. Everything is, we put everything in a parameter file. It makes it easier to change things and rerun simulations. So that's what we have done here. So you can see that we join these two voltages together to form essentially the complete PWM, back EMF signal. Okay. So we'll see the parameter file. We'll also see some of the waveforms. So this is your complete BLDC model. So you have got essentially per phase. So you have got phase A, phase B, phase C. You have got series inductance, resistance for 3 phases, and everything is we even define inductance as L-MOT. Now the beauty of this is that if I put it on a schematic, I have to change it 3 times, 3 places when I change it. But when I have a parameter file, I just change it 1 time, and all of them are changed. Right? So that's the time saving you have. And same thing is true with the when I change the back EMF amplitude, I just change 1 parameter in the parameter file, and we're done. Right? So this is how we generate the BLDC. This is the BLDC model, right? And then of course we have the neutral connection at the bottom. And now here, you can actually see the delays. This is not updated because they were later replaced by delay 1, delay 2, or so on and so forth. But you can see that the delay for this particular waveform to come up is 1 by basically third of the time, because 1 by frequency is your time period, so it's third of the time.
But also can be taken as 1/3 of the frequency.
That's correct.
Another variable.
It is on another variable. That's how it is set. The parameter file it is set as 1 by 1/3 of the time period.
1/3.
Yeah.
The amplitude here would it not be a function of the speed?
Yes.
It looks like it is the parameter here, not a variable.
Yes. Now, in this particular model, we'll show the parameter file. Yeah, it is a function of the frequency. It is a function of the frequency. So when this is of course when you're developing a complete model where we also have mechanical components incorporated and the frequency is variable, then we include that as a function of speed.
Now there is no speed inside.
Pardon me?
It's only an EMF equation.
It is only an EMF equation. That is correct. That is correct. Okay.
And can this model be used for speed control? It cannot be used. I can't have a speed control.
You can have a speed. Yes, you can.
Here,
Yes, you can.
the same model.
The same model. Yeah.
Where is the speed parameter?
See here now the speed. Okay. Let's see. See let me use this one here. So we have currently we have got essentially constant speed operation. Now, so back EMF is a function of, let's say right now we're running at 133 hertz. That's about it. It's a function of 133 hertz, right? So this is basically a constant Ke omega, right? Now, in PSpice, we can, right now we have defined in the parameter file A is equal to something like 6.3 volts. Now what we have in this particular demonstration, we are only showing constant speed operation, but you can easily replace A with intertwined parameter. You can have a parameter, essentially it is a function of, so I can define, you can either do ABM, which is analog behavior model, where I have a speed, and we'll see that in induction motor drives, when we do the simulation for induction motor drives, we have demonstrated how you can incorporate speed into your model. But this one particularly is a constant speed model, but you can take omega as an input, and with an analog behavior model, you're able to essentially get Ke omega. And then Ke also is a constant you can define. Yeah, is a constant you can define. So in this particular model, the constant speed model, basically because we want to illustrate, one is ideal components. We want to illustrate the PWM, which we're going to talk about in a minute. We want to illustrate the PWM function is critical. And I think what we have is quite beautiful. The ideal switch, the ideal diode. Those are the three components which actually we use quite extensively in building our models. And those are what I call convergence robust. Okay. So, but it's quite easy. Same model you can use for variable speed as well. And let's see here. We have, yeah. So what I want to illustrate really is that we have got an ideal switch, an ideal switch diode with snubber. There is an inbuilt snubber on this diode that helps in convergence. It is not shown here, but this diode has an inbuilt snubber, a very small inbuilt snubber, which will allow you to simulate faster and avoid any convergence issues. Now, I have shown here this here. You can ignore it's really not relevant that we bring the neutral out and trying to connect this. It doesn't really have any significance. So don't think too much into this voltage being divided into two sources. It's relevant in sinusoidal drives where the neutral floats to half the DC voltage, but not in this case. Questions? No? Okay. Now, we like parameter file quite a bit because it allows ease in simulating. Now, you can also put all your parameters on your schematics as well in PSpice. But we like to put it as a separate file, number one, because it can be used in other Spice programs. And so we try to reduce our dependency. We can create a netlist from OrCAD and run on other Spice platforms, which is what we try to do with because we don't have any relationship or any strategic relationship with OrCAD. So we tend to produce our models which can be used across platforms for Spice-based systems.